Hello everyone, I'm Nem and welcome to my lab experiment on slinkies. So the purpose of this experiment is going to be to observe the motion of a stretched out falling slinky mass which is dropped from rest and displays characteristics of drag. We're going to identify how tension forces cause the bottom part of the slinky to seemingly stay at rest while the top part of the slinky falls extremely fast. We're going to compute this using our coding. Some brief overview results is that the top of the spring is going to fall to the bottom part of the spring, and when they meet, they'll both fall simultaneously together. While the top of the spring is falling, the bottom part will stay suspended in the air as the tension force and gravitational force balance each other out. So first we're going to talk about the scientific principles which are going to be in this experiment. First we have to know Newton's second law so that we can accurately update the velocity and position as we're going through the coding. Then we need the gravitational force because the slinky is falling towards Earth in j hat direction of mg magnitude. Then we'll talk about the drag force, which of course is going to cause a little bit of resistance to the gravitational force, so it won't fall exactly mg, but it will also have the drag force opposing it according to Newton's third law. And then we're going to talk about how the gravity force and tension force will oppose each other, again because of Newton's third law. And also we're going to make some assumptions that the information that Dr. Greco gave us in the experiment is correct in our coding. Next we're going to talk about the tension force, which happens when a mass is applied in a direction that's away from the original mass. And the tension force normally develops in rope, string, and cable. In this experiment it's going to be a string. And it's acted along the length of the sling in the direction that is opposite to the force applied to it. And as the pulling of the top increases, the tension on the bottom part of the slinky increases. The initial conditions in the experiment are VI 000, T naught is 0, and the original position is just this random number that Tracker gave me. The system in here is going to be the slinky, and the surroundings are the atmosphere, aka air resistance and wind, Earth, and his hand in the experiment. Okay, and now here's just a video of him dropping the slinky. So these are the graphs that came from GlowScript and from Tracker. So the one in the top left is going to be from GlowScript, and as you can see, it displays characteristics of drag, and also just kind of shows how the bottom of the slinky doesn't originally start moving until it gets hit by the top slinky. And then the bottom left shows the top slinky, which just moves linearly down, while in the top right it shows that the bottom part stays still and then moves linearly down with the top part of the slinky. Okay, so now I'm just going to show you the initial conditions of my coding. The ball mass given by Dr. Greco was 0.25 kilograms. The initial positions, again, like I said earlier, and then t is equal to 0. Delta t is 0.001 because this experiment did have been super duper fast. G is 9.8, like it always is, the constant. J hat is going to be 0.10, and then the drag force is going to be 30.85. Okay, now moving on to Newton's second law updating. We have that the work is going to be equal to negative mass j hat times g. The drag force is going to be the negative b constant from earlier times the magnitude of the velocity squared times negative j hat, and F net is going to be work plus the drag force. And then this is the ball velocity and ball position update formulas from earlier, which came from Newton's second law. And then advancing the clock is just t plus delta t for each subset division of the time. Okay, and then lastly, I do want to mention the errors. So for finding the drag constant, I used a lot of guessing and checking, which obviously could not have proved to have the most accurate results. And I also hand selected the center of the mass on Tracker, which obviously is going to have a lot of human error. Then we have my free body diagram on the left, which shows that force of tension is going both upwards and downwards. However, Fg is also going downwards. So basically how this works is that Fg and F tension are both going down. So the top has basically like double force going down, while the bottom has F tension going up while Fg is going down, and so those cancel out. So the top has double force while the bottom one has no force, which is why it seemingly kind of floats in air. So the big picture, why did the top of the slinky fall first? It's just that the slinky has stored energy from the spring function that matches gravity exactly, and when the slinky is stretched out and the top is held, the bottom is being pulled up with a force equal to the gravity pulling it down, and that's why it only stretches out so far. And when the top is released, the bottom is still being pulled upward by the spring function or the tension force until the slinky stored energy is gone when they collide, and that force of contact just causes them both to fall really dramatically and quickly. Thank you so much for watching. Have a wonderful day.